So hello everyone, this is lecture 6, Limits at Infinity. Before getting to the main topic, I want to give you a motivations example of where is the limit at infinity coming from. So in pre-calculus, you learn about the end behavior of the functions. That is, when you let x go to infinity, you want to know what is the y value is going to be. Or when you let x to negative infinity, what is the output of the function is going to be. So that is going to be the same idea here in the context of limit at infinity. So given the graph of the functions right here, we want to find the following limit. That is limit of f of x as x approaches 2 from the right, limit of f of x at x approaches 2 from the left, then the limit of the function at x approaches negative 1 from the right, and limit of the function as x approaches negative 1 from the left. When you look at the graph, the limit of the function as x approaches 2 from the right is going to be here. So the functions go down to negative infinity. So the answer here is negative infinity. Now, the limit of the function as x approaches 2 from the left, as you can see, the function's going up to positive infinity. So here, this is what you got for positive infinity. In addition, the limit of the function as x approaches negative 1 from the right, the function's going down to negative infinity. And the limit of the function as x approaches negative 1 from the left, you have the functions going up to positive infinity. So the result you have here is called infinite limit. Here we call that infinite limit. Now, using this information, you can conclude about the vertical asymptote of the functions. So the vertical asymptotes are x equal to negative 1 and x equal to positive 2. Now, what about this behavior of the functions as x approaches positive infinity and as x approaches negative infinity? What is the function approaches to? So here in the context of limit, you have limit of the function as x approaches negative infinity. You have the function approaches this horizontal line. And by the look of the graph, this horizontal line is equal to 1. Similarly, when you consider the limit of the function as x approaches positive infinity, so the function approaches this horizontal line, and that line again is equal to 1. When that is the case, or when either of these cases occur, you conclude that y equal to 1 is a horizontal asymptote. And that is the motivation for this lecture. That is, when you have x go to either negative infinity or positive infinity, you want to investigate the end behavior of the functions. And these are called limit at infinity. And when limit at infinity equal to a constant, then you can say that y equal to that constant is a horizontal asymptote. Now let me move on to the next topic.
All right. So that brings us to the definitions. Limit at infinity. Let f be a function defined on some interval a to positive infinity. Then the limit of the functions as x approaches positive infinity equal to L. This means that the value of the functions of f of x can be made arbitrarily close to L by taking x sufficiently large. Similarly, you have let f be a function defined on some interval negative infinity to a, Then you have the limit of f of x as x approaches negative infinity equal to L. This means that the values of f of x can be made arbitrarily close to L by taking x sufficiently small. And then the last note I have here is y equal to L is the horizontal asymptote of f of x if either the limit of the functions as x approaches negative infinity equal to L, or the limit of the functions as x approaches positive infinity equal to L. So let's take a look at this example. I consider the graph of y equal to arctangent of x. So this is the graph. This is x, and this is y, this is pi over 2, this point, and this point is negative pi over 2. And the graph of the inverse tangent functions looks like this. So the orange curve is y equal to tangent of x. Right. So by looking at this, you can see that the limits of the functions are tangent of x as x approaches positive infinity, right, is equal to pi over 2. Right? So you have y equal, so this implies that y equal to pi over 2 is a horizontal asymptote. Right, similarly, right, usually when you look at the horizontal asymptote, you have to look at when x approaches positive infinity or x approaches negative infinity. Right? So when you consider the limit of the arctangent or tangents as x approaches negative infinity is equal to negative pi over 2, so you also say that negative y equal to negative pi over 2 is a horizontal asymptote. All right. So another example, most of the time you don't have that luxury of having a graph, right? So you have to do this algebraically. So how to do that? Right. So for this example, I'm gonna say that find the following limits. So limit of 1 over x as x approaches infinity, and limit of 1 over x as x approaches negative infinity. So what's that going to be? Limits of 1 over x as x approaches positive infinity, right? So x approaches a very big number, and that is in the denominator. When you do substitution, you will get 0. And similarly, you have limit of 1 over x as x approaches negative infinity is also equal to 0. Even though you approach a very big negative number, it's still in the denominator, so you have 0 for the answer. Right? So can you evaluate the following limits? The limit of x approaches infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. Right, for any limits problem, the first thing that you can do is you use direct substitutions. Right, you just substitute when you let x go to infinity in the place for x. See what you got. Right. So 3 times x squared, so 3 times infinity squared, and then minus infinity minus 2. I could say that by direct substitutions. Right? 3x minus 2 over 5x squared plus 4x plus 1 as x approaches infinity. Right? If you use direct substitution, you will have infinity over infinity. So when you substitute infinity in the place for x, right, you have infinity squared, which is very infinity, right, very big number. Subtract another big number, but infinity squared will dominate. But just to be clear, infinity is not a number, it's a concept. Just to say that we are approaching a very big positive number, right? Let's say a trillion, right? Instead of saying some weird infinity sign like this, you can substitute in a trillion, right? Like 3 times a trillion squared and then minus another trillion minus 2. The 2 doesn't matter in this case because we're talking about a very big number, right? So something that is very big positive square going to be infinity again, right? So the numerator is infinity. It just say that the numerator will give you a very big positive number, right? So similarly in the denominator, you substitute like a very big positive number, you could get positive infinity again. Right, when you have infinity over infinity, this is another indeterminate form. Now, when you have indeterminate form, you need to do something. You need to make some cancellation and whatnot, right? So that you can get rid of this indeterminate form. Just like we use direct substitution, we got 0 over 0. Right? That also the indeterminate form. You have to simplify somehow to get rid of that form. All right, so for this particular problem, what you can do is take out the highest degree in the functions as the common factor and try to simplify that. So what do I mean by that? So from the original limits, we have limit as x approaches infinity. So on the numerator, the highest degree is x squared. So you have x squared as the common factor. You're left with 3 minus 1 over x minus 2 over x squared. Over x squared times 5 plus 4 over x plus 1 over x squared. Alright, so now I'm going to cancel out the x squared, and I left with the limit as x approaches infinity of 3 minus 1 over x minus 2 over x squared divided by 5 plus 4 over x plus 1 over x squared. And you remember the limit laws, limit of the sum with the sum of the limit, and so on and so forth. And this is the quotient. Limit of the quotient is the quotient of limits. So you can take the limit on the numerator and the limit of the denominator and so on and so forth. So the limit as x goes to infinity of 3 minus 1 over x minus 2 over x squared divided by the limit as x approaches infinity of 5 plus 4 over x plus 1 over x squared. Limit of 3 as x goes to infinity minus the limit of 1 over x as x goes to infinity minus the limit of 2 over x squared altogether divided by limit at x goes to infinity of 5 plus the limit of 4 over x goes to infinity plus the limit as x goes to infinity of 1 over x squared. Right, so the limit of 3 is going to be 3, right? The limit of 1 over x as x goes to infinity, 0, thank you. So this is minus 0. What about the limit of 2 over x squared as x goes to infinity? So minus 0 as well. Now altogether divided by 5 plus 0 plus 0. So hopefully you get that, right? So the answer is 3 over 5, right? Because the limits of the functions as x goes to infinity equal to 3 over 5, you say that y equal to 3 over 5 is the horizontal asymptote. So sometimes you may not be able to find the horizontal asymptotes. For example, in this case, so find the limits of x squared plus x over 3 minus x as x goes to positive infinity. So you do the same thing by direct substitutions. You have limits of x squared plus x over 3 minus x as x going to infinity. So what you have is positive infinity on the numerator and negative infinity on the numerator. Right. So if not, this is still indeterminate form. Okay, so when you have indeterminate form and x go to infinity like this, you take the highest power on the numerator and the denominator and then simplify it as much as you can. So from the original limit, you have limit as x go to positive infinity. So x squared is the common factor, and you're left with 1 plus 1 over x. And the highest degree in the denominator is x. You have 3 over x minus 1. You simplify it and you're left with limit as x approaches positive infinity of x times 1 plus 1 over x divided by 3 over x minus 1. So what is the limit of this function 3 over x as x approaches infinity equal to? Should be 0, right? So when you look at this one also 0, this one is also 0. So all right, so what I can do is redistribute x into the parentheses so you can see it better. So x plus 1 over 3 over x minus 1. The limit of 3 over x is going to be equal to 0, and you're left with infinity over negative 1, which is negative infinity for the answer. Right, because the limit of the functions approaches, big negative number, it's not a constant, so that shouldn't be a horizontal asymptote, right? Or you can say the limit does not exist. Right, so another important example, find the limit of e to the x as x approaches infinity, limit of e to the negative x as x approaches infinity, the limit of e to the x as x approaches negative infinity, and limit of e to the negative x as x approaches negative infinity. This is some of the important limits that you should know. All right. So the first limit, right? Limit of e to the x as x approaches positive infinity. Right. So exponential functions, right? Infinity is a very big number. E to the infinity is going to be a huge number, right? So this should give me infinity. Now for limit of e to the negative x as x goes to positive infinity. So e to the negative infinity, right? E to the negative infinity, right, is the negative exponent. You can turn to the positive exponent as this 1 over e to the infinity. Infinity is a big number. E to the infinity is a big number. 1 over the big number. What do you got in this case? 1 over infinity. What is 1 over infinity going to be? 0, right? If you're not sure about this, you can work out very quickly the idea of 1 over a very big number. So for example, if you have 1 over 1 is 1, 1 over 10 is 0.1, 1 over 100 is 0.01, 1 over 1000 is 0.001, right? So as you're dividing a very big number, the result gets smaller. That's the idea of 1 over infinity. Okay. So next, the limit of e to the x as x approaches negative infinity. So this gives me e to the negative infinity. So e to the negative infinity is 1 over e to the infinity. And what is that equal to? 0. Limit of e to the negative x as x approaches negative infinity of e to the negative infinity. This should give me e to the positive infinity or infinity for the answer. Another limit that we should look at is the limit of sine and cosine functions. So find limit of sine of x as x approaches positive infinity, limit of cosine of x approaches positive infinity. Same thing when you have limits of function as x approaches negative infinity. Right. So as you remember that the sine and cosine functions are periodic functions. Right? So it goes on forever. Right? It goes on forever. So when you want to find the limit of this function as x approaches either positive infinity or negative infinity, you cannot find the limit. Right? In other words, the limit does not exist. So what you can say is the limit does not exist for any of this any of these limits. Okay, because sine and cosine functions um, go on forever to infinity or negative infinity. So that's why the limit does not exist.